19. Yeah.
So 10 years with the
It's still
pandemic.
2020, right? So, yeah, we don't know. Stephanie got her bachelor's degree in geography from Indiana State University, which is where you grew up in Indiana too, except originally Columbia, right? And so that's Indiana is probably not a lot like Columbia. Nice straddles and nice gradients there. Climate, topography, all sorts of things, right? But after finishing her bachelor's degree, she went to Colorado State, where she received her master's and PhD, and then was a postdoc here in the Center for Climatic Research, and then has been on the faculty. As I mentioned, Stephanie's work spans a whole variety of topics on tropical and extratropical interaction, climate and multiple timescales, and today we're going to hear about one of those, which is the optimal development of the Pacific North American pattern. Got it, I'll pass it on to you.
Thanks, Hunker. Should we dim the light? Can everybody see?
Yeah, we can do this.
That's
Okay.
Yep.
All right, thank you so much for the introduction. Can everybody hear me? I'll do my best to project. If you can't hear me, just let me know if I start getting soft. So thank you so much for giving me a chance to present some of this work. I actually did this work during my postdoc in CCR with our Professor Dan Beaumont, but I had never presented it here, so I thought the CPEP talk would be the optimal opportunity to present my CCR postdoctoral work. And this is work that we did in collaboration with Madden-Julian. I'm going to be largely focusing on the role of the tropics on the development of the PNA pattern. But before we get into that, what is the PNA pattern? So what you see here are the two phases of the PNA. We have the positive PNA on the left and the negative PNA on the right. The color contours here are showing upper level stream function anomalies. So in red we have anticyclonic anomalies. In blue we have cyclonic anomalies. So the PNA pattern is often thought of as this kind of this pressure quadrupole, this wave train that you see here. So in the positive phase we have this high, low, low. And then during the negative phase we see something very similar but of the opposite sign. Now this pattern is most prominent during our winter time, so December through February. And what you'll notice is that over North America, we get some anomalies that are very similar, but of the opposite sign between these two phases. So not surprisingly, the PNA pattern will, depending on the phase, will have the opposite impacts. So that leads us to why should we care? Why do we care about the PNA pattern? So just for reference, I put the really small up here, the PNA pattern that I just showed you in the last slide. And what you see here is the relationship between the PNA and temperature at the top and precipitation at the bottom. So the color sign that you see here would correspond to the positive PNA phase. So during the positive PNA phase, we see warmer than normal temperatures across much of North America and colder than normal temperatures across much of the southeast. For precipitation, you can see that we have suppressed precipitation in parts of the Rockies as well as the Ohio and Mississippi Valley regions. We see enhanced precipitation in the Alaskan Gulf and Canadian coast here, as well as the Gulf Coast. And then during the negative PNA phase, we see very similar impacts, but they will be on the opposite side. Right, so given the impacts that we see, the impacts on temperature and precipitation that we see associated with the PNA pattern, this leads us to the conclusion that it's important to understand what leads to the PNA pattern. That way we can better predict it and understand the anomalies that we see over North America. Okay, so prior to this work, we of course dug into the literature and asked the question, what has been done to understand what leads to the PNA pattern? So what we found is that there's been a few phenomena that have been independently linked to the PNA pattern. In the tropics, there's two tropical phenomena. One is the El Niño-Southern Oscillation, or Enso, and the other is the Madden-Julian Oscillation, or MJO. Outside of the tropics, studies have also examined just purely focused on mid-latitude variability and its and the evolution of the P&A pattern, kind of not looking into the tropics, right? So these three are kind of the main story within the literature, but they're typically looked at separately. So I'm going to be focusing quite a bit on the tropics, as I mentioned earlier. So I'm going to give a brief introduction to Enso and the MJO, for those of you that maybe are a little bit less familiar with it. So Enso, what you see here are the two phases of Enso. Enso is most prominent during winter months, DJF. And what you see here at the top is what we typically see during La Nina conditions, and then at the bottom is what we see during El Nino conditions. So in the color shading is anomalous sea surface temperatures, or SSTs, and then in the black contours are the precipitation anomalies. So during La Nina, we typically see colder than normal sea surface temperatures and suppressed precipitation. Whereas during El Nino, we see warmer than normal sea surface temperatures across the Pacific and increased precipitation. And we see the opposite then over the Western Pacific. Now, what's important to keep in mind for this study are timescales. Enso is persistent, right? It impacts us for a full winter season, right? For example, this past winter, we've been in a La Nina. I think we still are in a La Nina, right? So Enso gives us a seasonal, it's a form of seasonal variability, right? It's persistent, it'll impact us, for example, for a full season. That's quite different from the other form of tropical variability here, which is the MJO. So I like to show this animation every time I explain the MJO because it's great. What you see here in the color shading are precipitation anomalies. So during a typical MJO event, what happens is we get enhanced precipitation over the West Indian Ocean, so you'll see that right here, and then that propagates eastward over the maritime continent and into the Central Pacific. And you'll also notice that that region of enhanced precipitation or convection is preceded and followed by a region of suppressed convection in the reds. Now this whole MJO life cycle lasts on average about 40 to 50 days. You can see a 48-day cycle going through here at the top right. And because the MJO is an eastward propagating system, it is really helpful to define an MJO phase. So you can see those cycling at the top here too. So MJO phase 1 is when that enhanced convection is over the West Indian Ocean. And then by MJO phase 8, that enhanced convection has reached the Central Pacific. So an MJO phase will tell us where the MJO convection is at any given point in time. Now, each MJO phase lasts on average about 5 days. So MJO gives us a means for a weekly variability, right? This weekly variability will give us weekly predictability. So how is it that these tropical phenomena, and the MJO, impact us all the way up here over North America? So both the MJO and Enso trigger these large-scale waves known as Rossby waves. And I like to show this video showing this. This is an animation from Isaac Held, and it's a toy model. It's very idealized. But what he does is he places a forcing in the tropics. It's a divergence, upper level divergence forcing, which would be associated with deep convection. And then what you see then is the response to that forcing as I play this. And you see this propagation away from the forcing and into the mid-latitudes and high latitudes. So these are known as teleconnections, right? These Rossby waves form teleconnections because they connect remote regions of the world. Both MJO and Enso force these type of teleconnections, right? But remember, they operate on different timescales, right? So Enso will persistently force a particular teleconnection pattern, whereas the MJO, as it propagates eastward, its teleconnection patterns will change. And I'll show you those in a moment. In reality, too, the hemispheres are not dissymmetric. They just are for this toy model. Okay, so here we have the Enso teleconnection. So the top is El Nino, at the bottom is La Nina. And this is showing upper level geopotential high anomalies. So During El Nino, what we typically see is a cyclonic anomaly over the North Pacific, and then an anticyclonic anomaly over North America, and then a cyclonic anomaly. So this is the wave train that propagates as a result of the enhanced convection associated with Enso. During La Nina, we see the opposite anomaly over the Central Pacific. Right here we have an anticyclonic anomaly, and then we see a slight cyclonic anomaly then over North America. Right, so now again, always reminding you of this time scale because this will become important, right? Enso is persistent, right? So these teleconnections will be persistent during Enso events. Okay, now let's look at the MJO. So here we have MJO Phase 3, which is, if you look at the tropics, this is when we have enhanced MJO convection over the East Indian Ocean and suppressed convection over the Western Pacific. And then you can see the upper level 250 hectopascal geopotential height anomaly. So we get this kind of high, low, high. And my green arrow there just showing the direction of propagation, right? This Rossby wave propagating away from the source region. Now, I mentioned each MJO phase lasts on average about 5 days, and that's an average, it varies. But it also depends on where the MJO convection is. So let's look at a different phase. So here is the plot that I just showed you on the last slide, right, MJO phase 3. Now about 15 days later-ish, we get MJO phase 7. Now MJO phase 7 is characterized by suppressed convection in the West Indian Ocean and enhanced convection in the East Indian Ocean and enhanced convection in the Western tropical Pacific. So you'll notice that MJO phase 3 and MJO phase 7 are very similar, but they have convective anomalies of the opposite sign. Now surprisingly, and not coincidentally, you end up with the opposite sign teleconnection pattern over the Pacific. Right, so here at phase 3 we have this kind of this high and then a low and then a high, whereas here we can see that now we have this low and then a high. They're not perfectly symmetric, of course, but you can see they're very similar but of the opposite sign. Right, so during an MJO event, an MJO can force this particular teleconnection pattern, and about 15 days later, it can force the opposite sign teleconnection pattern. Yes?
How long does it take for that teleconnection pattern to get established? Because
yep, it takes
things
time.
are moving
Yep.
around. Right?
Yep. So if focusing on the Pacific, you can see it within like 5 to 10 days, and over reaching to the Atlantic, it's more like 10 to 15 days. So it's for it to be fully established in the extratropics, it's between like a week to 2 weeks. So these composites are looking at, I think it's 5 to 10 days after each phase. Yes?
So, a similar question. These geopotential anomalies persistent and the downstream anomalies have formed in downstream development, or is it that the MJO forces a trough or a ridge and then that propagates downstream and I can track the individual?
You can, so the Pacific is very linear. Like if you, you can just force the Pacific anomalies entirely from the MJO itself, like with a simple model where you just input a heat source and this is what you get. Over North America, you start to get some nonlinearities that take place, partly due to topography, and composites also help to average out the noise, right? So in reality, if you look at individual events, there are going to be differences due to internal variability, interactions with whatever else may be going on, but the composite kind of helps to try to average some of that out. Yes?
Just one question. Just
Sure.
you get to the end of an MJO life cycle, like you're at phase 7, does that give an advantage to the establishment of the anomaly field that characterizes phase 7 versus at phase 3 when you're in the flux as the active and inactive convective regions are moving across the Pacific and Indonesia? Here they're getting to the end of their life cycle. Is there any advantage to that in terms of the longevity or imprint that's made at this point?
So it's tricky because MJO is really noisy. So you don't typically get a case where an MJO strengthens during phase 1 and then persists and stays strong all the way through MJO phase 8. Typically, it's more like, okay, we'll be really weak, and then suddenly phase 4, and then by phase 7, then it'll weaken. So it's actually really noisy, which is why I like to look at lags as opposed to like lag 0 composites, because it takes time, as Michael said, for that signal to kind of get established up there. And the tricky thing too is as you get to later MJO phases, you also have impacts from previous MJO phases. So it's actually simpler a lot of times to look at the early MJO phases for that reason.
Oh, okay. Thanks.
Yep. Okay, so going back to this slide, right, so here we have, in the tropics, we have Enso, which gives us seasonal variability, MJO, which gives us weekly variability, and then I haven't really talked too much about this, but you also have internal mid-latitude variability. And so what we want to do in this study is not look at them independent of each other. We want to do a comprehensive analysis where we consider all of these processes. And what we do is we ask the question, okay, if we allow all of these processes to coexist, and we consider these different possibilities, what is the optimal way to get to a peony pattern? If we allow all of these different ingredients to exist and consider all of these different ingredients, is there an optimal way to get to a peony pattern? So to do this, we have to specifically include data that will capture all of these phenomena. So we focus on DJF. DJF is when the PNA pattern, Enso, and the MJO are the most prominent. All of our data is 5-day average to reduce some of the noise. And these are the data sets that we look at. So we have, in the tropics, we have tropical SST and tropical heating. So tropical heating is associated with convection. So both of these tropical data sets will capture Enso and the MJO, which we know may be important for the PNA based on the literature. In the exotropics, we include a stream function in the upper and lower levels to capture the evolution of the PNA pattern. And then what we do is we use something known as linear inverse modeling. I'm not going to go too deep into the background of the LIM, though I'm happy to for anybody who's interested to chat about this more offline. I'll just talk a little bit about it and provide a little bit of background. So LIM, what it does is it assumes that the state of the system, which we call X here, so X includes all of our data sets, so tropical SST, our heating, and our stream function, all of that goes into X. All of our data sets are EOF truncated to focus on the large scale variability and kind of reduce some of the noise. And so all what's included here are the time series of those EOFs, so the principal components. So here's where all of our data goes into X. And then what LIM does is it assumes that the time evolution of X is split into these two components, a part that's predictable and a part that's unpredictable. So here we have the predictable dynamics, and then the unpredictable part would be the noise. Now in this study, I'm going to be focusing on the predictable dynamics, not that the noise is not important, but we're just not going to consider it at this point. Now, in order to find what X is at some later point in time, so some lag tau, what we do is we focus on this first term here, and this X at a later time is simply given by an initial condition, X at time 0, times this G here, which we refer to as a propagator. Now what is this propagator? It's simply the lagged covariance of X divided by the simultaneous covariance of X. So what does this mean? This means that G is a matrix that contains information about how all of these data sets here, how they vary and how they co-vary with each other. So this is including the statistics to try to understand the relationship between these different data sets. From that, we can back out L. So you can see L up here in our original equation. So we just compute the natural log of G and divide by our lag. That's how we get L. And then from that, our initial condition times e to the L tau will give us then some X. Okay, so just a little bit of background. I don't want to focus too much on the math. But again, if anybody wants to learn more, just let me know. Okay, so what makes LIM awesome? Well, that is a big question, and there's lots of answers to that. But one particular thing that you can do with LIM is makes it really different from, for example, when you think of a typical forecast. So if you think of a typical forecast like using a statistical model, you have some initial condition at time 0, and then based on the predictable dynamics of the system, you get to some final condition after so many days, right? Forecasts move forward in time. Now, a really cool thing you can do with the LIM is you can go backwards. So you can say, I want to get to a very specific final condition after so many days. In our case, that would be the P&A pattern. And then based on the dynamics of the system, how do we optimally get there? So we're looking for that initial condition that will optimally get us to our final condition of interest. So we're prescribing the final condition in order to find this optimal initial condition. For those of you that are curious as to how we do that, this is the answer. We solve the eigenvalue problem to do this. So we find the optimal initial condition by maximizing the growth in the direction of the P&A. And then the optimal initial condition would be the eigenvector with the largest eigenvalue. Okay, so let's look at some results. So we're looking at growth over a period of 15 days. So this is our final P&A pattern, right? So here you can see that P&A pattern here, the color shading is our 200 millibar string function. The contours are the 850 millibar string function. And what you see is a P&A pattern, and you should, right? Because we prescribed it. We told it to grow a P&A pattern, so this should look like a P&A pattern, and it does. What we were looking for is this final condition, or excuse me, this initial condition. So this is the string function anomalies that optimally get us to that final P&A pattern. Now we don't see too much here, right? We see some anomalies that are weaker relative to our final condition. We see this, there's an anticyclonic anomaly here and another one over here. We can look at the time evolution of this to see how this initial condition gets us to that final P&A pattern. So this is day 0, it would be the initial condition. During day 1, you can see this anticyclonic anomaly in the Northeast Pacific that over time retrogrades to become part of our final P&A pattern. We also see a cyclonic anomaly that develops in the subtropical Pacific that becomes part of our P&A pattern. Right, so we can see this kind of evolution of how exactly did this become this. Now there's another piece of the puzzle, which are the tropics. So what are the tropics during over this 15-day period? So in the color shading, we have our heating anomalies. So where you see positive heating anomalies, that's a region of enhanced convection. So we have some enhanced convection in the Indian Ocean and some suppressed convection in the Pacific. And then 15 days later, this enhanced convection has shifted eastward. And then this suppressed convection is then across the Pacific here. The dashed lines are showing SSTs, so you have cold SSTs associated with this. This should look really familiar, right? That is associated with the La Nina. And we can verify that by looking at the time series associated with this pattern. It's a little easier to look at what's going on if we look at a longitude time diagram. And we can actually evolve this beyond the 15 days. So 15 days is when our P&A pattern develops, but we can kind of keep looking at the evolution beyond this to see, just to try to understand what patterns we're actually seeing here. So our initial condition is at day 0, and here you can see that the anomalies over the Pacific persist. So we have the SST and the heating anomalies across the Pacific, which will persist for the full 90 days, a whole winter season. And then we also see this eastward propagating heating from the Indian Ocean towards the Western Pacific. That's an MJO. So what this tells us is that the optimal way to get to a P&A pattern is when we have an MJO and an Enso occurring at the same time. Now, yes?
Is it important that the Enso wasn't there? It seems like it's right at the beginning.
Yeah. So there's some interesting things that happen. when we, so that's one thing we were really curious about is why do we not see an Enso here, but suddenly it develops? The reason for that we can actually examine the reason for that by separating Enso from MJO. So let me get back to your question in a moment, because we can't tell just from this point. So one of the really cool things that, again, you can do with LIM is you can separate the dynamics of the system. So we look at two subspaces of our dynamical matrix L. A coupled space, which would contain all of the dynamics that are strongly coupled to SST, which would of course include Enso, which is an atmosphere-ocean coupled system. And then an internal atmospheric space, which would contain all of the dynamics that are weakly or uncoupled with SST. So the MJO exists within this internal atmospheric space, right? Its existence does not depend on that coupling to SST. So what does that look like? So the way that this is done is by finding all of the eigenvectors and eigenvalues of L, and what we get are known as modes. So each of these circles are modes of L. Each of them represent either some independent process or a combination of modes. For example, these two up here are associated with Enso. You can plot them and see what they look like. This one here is the MJO mode. You can compute an E-folding time, which is the y-axis, and a frequency, which is the x-axis. And then based on this, how strongly coupled they are to SST, you get this natural separation that happens, where the coupled dynamics, the coupled modes, have this high E-folding time and low frequency, whereas the internal atmospheric modes have low E-folding times and a really wide range of frequencies. These modes are non-orthogonal, so this makes them very different from EOFs, right? If you think about an EOF, an empirical orthogonal function, they're required to be orthogonal to each other, right? So as a reason of that, it'll combine processes in order to meet that orthogonality restraint. Modes are non-orthogonal, so you can actually separate processes. This makes it really powerful and useful. So what we do is we separate them. We separate the modes that are coupled versus those that are weakly or uncoupled to SST. So this is the equation that does that. So here we have our optimal initial condition, and then we sum across so this is our optimal initial condition, right? When we include all of our modes, our full system, and then we separate it into the coupled component. So this is including only the modes that are strongly coupled to SST. So all of that, the coupled dynamics, and then the modes that are internal to the atmosphere. So this is excluding anything strongly coupled to SST, including Enso. But MJO would be within this subspace. If you add both of these together, we get our full initial condition. Now, just looking at these, you can tell why our initial condition is so weak, right? These two are of the opposite sign. So there's a lot of cancellation happening in our optimal initial condition. Now, what we can do is we can take both of these components and we can run them forward using our propagator G independently. So here we have our coupled space. This is the coupled component to our initial condition, and we run it forward by itself to get to a final PNA pattern, right? And this is, by the way, that PNA pattern when we consider all of the dynamics that I had shown you earlier. So you can see that here's our final PNA pattern. It is a lot weaker. And you'll notice too that our initial condition of our coupled component looks the same as our final component, except that there's some decay. And this makes sense, right? Because SST evolves very slowly, right? So we shouldn't expect a large shift in our circulation associated with coupled variability, right? Think about how slow Enso varies, right? Enso persists for a full season. So over 15 days, it makes sense that all we see is some decay. Now we can look at the internal atmospheric component, which includes the MJO. So what do we see here? The internal component in the initial condition, here we have an anticyclonic anomaly. Now it is substantially stronger. And we again see this anticyclonic subtropical anomaly as well. And then over the 15 days, we evolve that independently, and then we get our final PNA pattern. And now you'll notice that we have this flip of a sign between our initial condition and our final condition. Right, now if you think about the role of the MJO alone, this switch in sign over 15 days makes sense, right? If you remember back to when I showed you the MJO teleconnections, you do get this flip in sign over 15 days approximately associated with the MJO alone, though of course there's also mid-latitude internal variability associated with this, including this kind of pre-existing E-specific anticyclone, which is really interesting. And is the one that retrogrades to become part of our final PNA pattern. Okay, so let's put that all together. So here we have our initial conditions, coupled space and internal atmospheric space. So this includes the influence of Enso. This one includes at the bottom the influence of the MJO. Integrating them or not integrating them, but just running them forward with the propagator separately. We get our final PNA pattern from just the coupled component. Here is the final component, or final PNA from just the internal atmospheric component. And what we see is a slightly clearer picture as to how we get to that final PNA growth. So our initial conditions are largely of the opposite sign, and there's a lot of destructive interference happening between them, right? So we're minimizing the initial condition, the full initial condition, because these subspaces are largely canceling each other out. As the MJO propagates eastward and as these anomalies all evolve, this evolves towards constructive interference, where we now have anomalies of the same sign associated with these spaces, which will amplify the signal. And when we go from a really small, weak signal, where there's a lot of cancellation, towards an amplification of the signal, you get rapid growth, this maximum growth of the PNA pattern. With regards to your SST question, Brad, we saw the same thing with SSTs. So we in the coupled component, and I might have that, I'll check, but in the coupled component, there was that initial SST anomaly associated with Enso, but the internal atmospheric component had an anomaly of the opposite sign. And we do see, you can get an anomaly of the opposite sign associated with the MJO. So again, that's acting to kind of minimize that condition, but it's not a signal that we fully understand yet. That signal decays quickly, and then you just get that Enso signal that persists. And I can see if I have that at the end, that slide in my extra slides. Okay, so in this, one of the really cool things that we can also do, I keep saying this, I feel like I'm selling one, is in the same way that we filtered the optimal initial conditions in order to kind of understand the role of these different dynamics, we can filter X using the modes of the system, using the same equation, in order to filter the data so we can create a whole new limb that does not include Enso. So we can ask the question, you know, how do we get to a PNA pattern optimally in the absence of Enso? Because Enso keeps showing up, and it's really hard to separate MJO and Enso from each other. You can't do it with a traditional, you can try, but doing it like a frequency-based filter, you either have to sacrifice some MJO or include some Enso if you're doing temporal filtering. Okay, so what we do is we separate X into two components, a coupled component and an internal atmospheric component. So that will include the data that is the actual data sets and filtered based on the dynamics of the system. So let me show you an example. So here we have the 2007 through 2008 winter season. And I chose this season because it had both an Enso and several strong MJOs associated with it. So you can see this is a full data, so including everything. Here's longitude, and here's time on the y-axis. And heating is in the color shading. And then SSTs are in the contours, so you can see the La Nina event that happened in that season, persisting through the whole winter season. And then here are the MJO events that occurred that season. You can see them in the Indian Ocean and this kind of this tilt, this eastward propagation. So this is a full unfiltered data. So let's look at the filtered data. So this would be with the Enso removed, all of the dynamics coupled to SST, strongly coupled to SST, are removed. So you can see the Enso's gone. Enso is that persistent SST anomaly. The MJO is still here. We still see this kind of very similar anomalies. And you do get some SST anomalies. These are the SST anomalies associated with the MJO. So it can still interact with SST. And the MJO can still impact the SST, even when we do this filtering process. So the Enso is gone, but we still have an MJO. So what we do is then we create a whole new limb using just this data set, the filter data set. And we ask the same question, okay, let's grow a PNA pattern. And what we see, and this is the only plot I'm going to show from this, but here is the evolution of the upper level stream function. And what you see here's that anticyclonic anomaly. This is day 1, and then it retrogrades to become part of that final PNA pattern. And we also see the cyclonic anomaly that develops and grows within the subtropical Pacific. So it's a very similar evolution to what we saw earlier, right? Which tells us that a lot of that is largely driven by uncoupled variability and not by Enso. If we look at the tropics, here we see that Enso's gone, right? Last time we saw this really persistent signal, and that's completely gone. But we still get an MJO. We get this kind of eastward propagation associated with the MJO. So we can still optimally get a PNA pattern just from an MJO by itself in the absence of Enso. Okay, so what did we learn? So we found that the PNA could be a consequence of a few different processes. We have a slowly evolving Enso, right? Enso persists for the whole winter season. It evolves very slowly. And we have a far more rapidly evolving MJO that propagates eastward. And we also have some interesting dynamics going on in the extratropics, like that retrograding anticyclonic anomaly. Now, these all operate on different timescales to drive similar PNA-like anomalies at the end. So what we find is that strong amplification of the PNA, so that optimal growth of the PNA pattern happens when these various processes evolve from destructive to constructive interference. So when you get a lot of cancellation and then rapid growth, large amplification occurs when they evolve towards constructive interference such that the signal is amplified and you get this large PNA growth. With that, I'm happy to take any questions. Yeah.
Definitely have time for questions.
Yeah.
So, just thinking about the MJO for a second, I'm trying to pull my head out of like perturbation space and think about it just from like a weather systems perspective. And I'm wondering, what does this boil down to on a weather map? Do I just look for outflow of convection and isotropic chronogenesis on an isotropic surface, or is there, is it happening before my eyes and I should be able to identify it physically, or is it out
So
there?
you mean like as far as like the MJO teleconnections in general?
Yeah, exactly. Because I see the geopotential height anomaly retrograding, but
Yep.
I don't believe that a geopotential height anomaly itself can actually propagate. The geopotential height field has to do something in real time. And so I'm wondering, is that anomaly a ridge that's propagating upstream? I'm wondering how do I see this on the weather map?
So keep in mind that it is always trickier to see the influence of one particular phenomena on a weather map on a daily timescale, right? We often look at composites because it averages out a lot of the noise, and it lets us identify kind of a common signal between them. So regarding Rossby waves, that the teleconnections are just showing the Rossby wave propagation and how they look like on average, but in an individual case-by-case basis, it's not always as easy to see because there's other things going on. So, for example, I remember a case during La Nina, during La Nina, we typically get, La Nina often forces an anticyclonic anomaly over the North Pacific. And I remember very well, there was a time when we actually saw the opposite anomaly over the North Pacific, and everybody on Twitter was like, what is La Nina doing? This is not what we would expect during a La Nina, this is quite opposite, what's going on? And that goes back to thinking about the fact that there's other things going on too at the same time. At that time, there was actually a really strong MJO event happening, for example. And whenever you have multiple waves traveling in the same medium, they're going to interact, right? You can essentially add them together to get what the response is going to be, right? So you get a lot of destructive interference, and in that case, the MJO was really strong, so it actually had a bit of the MJO itself was forcing some cyclonic anomaly in that region. But of course, that's only part of the story, right? There's other stuff that goes on at the same time too. So it makes it really hard to kind of deconstruct exactly the role of everything. Which is why when we look at climate patterns like this, we often do things in terms of probabilities, right? So we say, okay, we're in an MJO phase 3, so we are, the probability is higher that we'll see these temperature anomalies at this location, or something like that, right? So it's statistical probabilities rather than something deterministic and something that you would get from like a numerical model. And these also operate on very different timescales, right, than your weather timescales, right? These are, an MJO phase will last for, on average, 5 days, although again, that varies. An Enso event lasts on way longer timescales than your synoptic weather, right? So there's a lot of other things going on to consider that makes it tricky to attribute to individual phenomena.
Can I carry on?
Sure.
So I guess maybe I'm going on the same vein, but if I have constructive Rossby waves in the mid-latitude geopotential pattern, right? That's what we're seeing downstream around the globe is an impact on the geopotential pattern of mid-latitude. So how do I marry the evolution of the geopotential pattern in the framework of the geopotential height tendency equation to Rossby wave energy? Like, I can add energy in one place, but the tendency equation says the only way I can deepen a trough is cold air advection, increasing towards the surface or diabatic cooling. So I don't know how to relate those.
Sure. So these are remote forces. The MJO, for example, will force a Rossby wave all the way from the tropics, right? So you have whatever is currently going on in the mid-latitudes. It's doing its thing. And then an MJO event amplifies, and then that will force a teleconnection pattern that will interact with whatever is already going on, right? So the MJO itself can force, if I go back to the teleconnection pattern, too far. So the MJO itself, if you remove, you can do this with a very simple model, where you just have some basic state, say the wintertime basic state, and you say, I want to just see what the impact of the MJO is by itself, not considering any interactions with like any flow interactions. We don't want to consider any other forms of variability that may be going on. We just want to know what is the specific impact of the MJO. There's models that you can use for that, and you can include an MJO and then see what the response is, and you get this wave train just from the MJO alone, right? So this would be adding those anomalies onto whatever is already there, right? So this would be, this would interact with whatever the extratropical geopotential height field already looks like, right? So you're adding, you're increasing the heights here, you're decreasing the heights here as a result of this tropical forcing.
Is that to say that I could look at a weather map at a given time and say that where the MJO precipitation anomaly is large, irrotational outflow, like I could just have straight zonal baritonicity, and I have irrotational outflow acting on isotells on an isotropic surface. I'm building a ridge right northward of my precipitation anomaly, and then I have downstream development of Rossby waves.
Yeah. I don't know how easy it would be to see on a weather map, but yeah, go ahead.
I think the better way to think of it is this is like an equilibrium solution of that. So it's still satisfying all the transient dynamics, but it's one where it's in balance, and it actually would sit there for a long time. You'd see transient propagating Rossby waves moving along there, but when you average everything out, this is what you end up seeing.
Yeah.
Because it's a stationary or quasi-stationary response to that heating.
Yep. Yeah, that's right.
That helps.
Yeah. Yeah, although what kind of makes MJO tricky is that
It evolves.
it evolves, right? So that even though if you just force it with, if you imagine the MJO is stationary, this is what you would get, and that would just sit there. It would be a stationary Rossby
Right.
wave. But because the MJO evolves,
It's moved.
it will change what the teleconnection pattern looks like. Yeah.
Yeah, I have a related question about, and this gets into the timescale of Enso versus the MJO.
Sure.
So I have two thoughts in my head for Enso regarding how it's setting up the geopotential anomalies, like its teleconnections. The first would be that Enso is setting up a standing wave the same way that MJO is here, and then that standing wave just has a much longer time scale because Enso has a longer time scale.
Yep.
The second thought that I would have is that Enso is modulating either the MJO or it's modulating mid-latitude dynamics, and so what you're seeing isn't actually a standing wave, but you're changing the probabilities. Like you said, it's
Yep,
a
you
composite,
are.
so you're just more likely to see one version than another. So I guess to what extent are those actually uncoupled for each other, and also like which one of those is more right?
With respect to MJO teleconnections or just mid-latitude dynamics in general, I can tell you that for MJO teleconnections, because Enso is persistent, right? If you imagine the impacts on the subtropical jet, right? During El Nino, you would have an extended subtropical jet. During La Nina, it would be a bit more retracted. And that's the Rossby waveguide than the much faster time scale MJO would experience, right? So if we have an Enso event set up, and then an MJO event happens, then the Rossby waveguides have an impact on what the MJO teleconnections look like. So there's two ways in which, the Enso will impact MJO convection. So for example, MJO propagates further eastward during El Nino events because you have that warmer SST. It also shifts the teleconnection patterns because of the changes on the subtropical jet. So during El Nino events, because the subtropical jet is extended, the MJO teleconnections will be shifted eastward. So that Rossby wave, that initial Rossby wave gets triggered within the subtropical jet, and then it's trapped within the jet until it reaches that exit region. Then it propagates into the exotropics. So the result is that the teleconnection pattern is shifted, whereas the La Nina one is further westward. So you get the shifted pattern. The other effect is the constructive and destructive interference. That also makes understanding probabilities difficult. Because if you have constructive interference, such as we have an MJO that is also forcing a cyclonic anomaly here, then you're going to have an amplified cyclonic anomaly. Whereas if you have destructive interference, such as the MJO is instead forcing an anticyclonic anomaly here, then you essentially have no predictability from either Enso or MJO, because there's a large cancellation. So you have to consider both to kind of try to understand the predictability associated with both, and which is why at times we often have what we refer to as like forecasts of opportunities. So it's like, oh, there's an MJO event happening. We have slightly greater predictability associated with that for this period of time. But what that predictability looks like does depend on what else is going on, such as are we in an Enso event. The tricky thing is that the more you kind of separate out your data, the less sampling you have. So that makes understanding the predictability impacts trickier.
This might be, so can you pick apart to what extent this pattern is due to like a background state versus a modulation of the more rapid?
With the Enso pattern,
Yeah.
how much of it is from the
like, how much of it is from actually changing the background state versus how much of it is from changing your statistics of, like, where the MJO is being placed, and then therefore that high frequency, if you're more likely to have the low over this region than the high versus in a La Nina.
So this specific pattern should largely average out any MJO. Because this is based on a composite of like a full winter season, so MJO should largely be averaged out. And again, this kind of goes back to like the concept of simple models that are used to try to understand the sole role of a tropical heat source on the extratropical circulation. People have done this where they'll say, okay, let's find out what the impact of Enso is by itself, not considering any other type of variability, and you get a teleconnection pattern that is fully attributable to Enso. And that these are really simple models where you just have linearized primitive equations about some basic state, and then you just have a forcing, and then all you get is the response to that forcing. So the simplicity of that is it's attributable. So you can get these teleconnection patterns from Enso heating by itself. Go ahead, John.
Fascinating talk, Steph. Thank you so much. I got a million questions. I'll only ask 8. No, I'll ask 2. One is, with the limb, it occurred to me that when you go from your final state and you're trying to identify your optimal initial state, it might be interesting, and maybe people do this, to see how does take an actual case of a fully developed PNA, positive PNA, and run it back using the limb as the guide to go back. How far away are you at day -5 from what the limb would show? And then start to characterize a whole season's worth of PNA developments and say some of them fit the limb model perfectly. So they really do obey all of the covariance stuff, and other ones don't. And then you might kind of be on the trail of what is it that gets in the gears of the ones that don't.
So people do use limb in a forward sense.
Yeah.
People can use it to make forecasts, and people have used it to make forecasts.
Yeah.
And they do really well.
Yeah.
This is something Matt Newman does quite a bit, is forecasting using the limb. Not specific phenomena like PNA, but rather just general forecasts going forward in time.
Yeah.
With regards to the PNA specifically, like there are some checks that you do, like for example, we check to make sure that this growth does actually happen within the actual data, and we find that it does. But keep in mind that what we found here is an optimal way to get to it, right? That doesn't mean it's the only way to get to it. Yeah. It's just how do we optimally get to that final condition.
Yeah, but even so, you could start to make statements about we're way off an optimal path here. And that's interesting.
Yeah.
Why is that? And then if I could just quickly throw in another one, could you make a matrix of, it'd be a lot of accounting, but you could say in MJO Phase 3, during an El Nino of a certain threshold, this is the standing pattern that you might see from the El Nino contribution, and this is what you might see from the MJO. And if a person, sometimes forecasters work that way. They have these matrices of combinations of things in their heads. They go to a 10-day forecast and say, well, I know I've got this phase of MJO and I've got La Nina. I see this standing pattern is kind of interfering in a positive or a constructive or destructive way. Has that already been done?
I've done that in a composite sense,
Okay.
not with the limb, but rather compositing by Enso and then by MJO, and then using a linear baroclinic model to kind of check that, where forcing an MJO, using a forcing of an MJO, but Enso provides the basic state to see, and that's where the results of the shifted teleconnection patterns come from.
Okay.
Was from the repetitive of that. But as far as the tricky thing again is that, so for example, one of the previous studies I did was looking at MJO and Enso impacts on blocking. Because of this complete change in teleconnection patterns, the shift in teleconnection patterns, and the interference that happens between the teleconnections, the impacts on the exotropics will change. And we saw totally different impacts on blocking depending on Enso phase. But sampling starts to get tricky, right? We barely had enough samples to for La Nina, for example.
Oh, yeah. Okay, yeah.
And so that's when things get tricky. Like, you know, as soon as you kind of add more interesting partitions, you know, the data gets more scarce. So that's the kind of the cautious part of doing stuff like that.
Great thought.
A bit of a two-parter question. How does the noise term in the ring model get calculated, and is there a trend in noise associated with the MJO?
So I didn't look at the noise for this study, but there's a lot of interesting things that people do with the noise. So for example, one of the things that can be done is people, so Erin Thomas was a student here, she did some of this work with Enso, is that you can look to see if there are certain noise patterns that can evolve towards those optimal initial conditions. So the noise can be used to kind of go a step further behind the optimal initial conditions to try to understand like the role of the noise essentially. And it's just a Gaussian white noise forcing. But with regards to the MJO, I don't know, I haven't looked at the noise for this. It would be really interesting.
Yeah, there's a question online from Matthew Hitchman. Does the PNA mature in the Pacific with the trough near Hawaii due to local dynamics or to the motion of the MJO, sorry.
Does the trough, go back to the PNA pattern. Okay, can you repeat that?
Yep. Does the PNA mature in the Pacific with a trough near Hawaii due to local dynamics or to the motion of the MJO?
Mm-hmm. So it's hard to directly say that because the internal atmospheric forcing included the MJO as well as mid-latitude variability that was decoupled to the ocean, but the MJO does force an anomaly in that region. So I think the MJO is capable of producing that subtropical anomaly on its own. As to whether it's the only way, I can't say that that's I cannot say that that's the only solution is that we get to that.
Yeah, just a really quick one, and it was actually about this particular figure.
Sure.
Is it fair to look at the positive and negative PNA patterns as opposite sides of the same coin?
Nope.
So when you sort of force, look for the optimal, what can you learn about the differences in positive and negative? Because I mean, the limit is linear.
Yep.
So the optimal is much different for the positive and negative phases.
So I specifically forced it with the negative, I grew towards the negative PNA. But the limb, because it's largely EOF based, the sign is arbitrary, right? So you can take all of your optimal and final initial conditions, and the sign will be associated with each other, right? But you can flip them all to get the opposite. I focused on the negative PNA pattern because it seemed to have the stronger link to the MJO and Enso. The positive PNA pattern, we saw similar results with the positive PNA pattern, but it wasn't as strong.
Okay.
And I don't know why.
Okay.
There is a shift, like you can see that there's a shift in the subtropics, so it could be that that there's a reason for that shift that we're not capturing, at least not well enough, and I don't know what exactly would do that.
So since these patterns aren't really opposites of each other, could they then represent fundamentally different dynamical structures?
Yeah, and over the Pacific, they're out of phase. So yeah, so they are so they would have different structures. Yeah, yep. I think that's a fair statement.
I think one more.
So, if I recall it correctly, the optimal initial perturbation for when you're forcing it to negative PNA looks somewhat like the positive PNA pattern. Does it say that the PNA is kind of cell cycling, like the positive phase would lead to negative phase, like 15 days later?
So the based on not this work, but based on composite analysis. So for example, the work that has previously linked into MJO by itself, The works that have previously linked MJO to PNA have found that certain MJO phases are associated with one phase, and then the kind of opposite sign PNA phases are associated with the opposite phase. So it is in a way you do see that kind of, that cycling where it goes from one to the other, at least certainly associated with the MJO, but the MJO itself is a propagating system, so you can get it from that.
All right, well, we're at time, so let's give hands to